And I don't want to listen to these stupid videos because they are just boring. They're so bad. I don't know how you guys make it 2 or 3 minutes into them. I assume you just zoom or scrub to where you get to what you need to see and then you're done, or hit pause. I don't know. Today we're going to talk more about angular momentum. And I did a demonstration on Friday before spring break. And although part of it got cut short because of the pep rally, I got through a lot of it. If you don't remember it, that's okay. Or if you weren't here, not less okay. But it was just a demonstration that I've done before. And many of you have seen it with me standing on the rotating platform and spinning this stuff. Do you guys remember all that? Fun times. I want to do a problem you have already done with a slight modification. So this is to get you thinking back to, physics and what it is that we've been doing before spring break. Let's do a merry-go-round. Let's say the merry-go-round is spinning 4 radians per second. Let's make that merry-go-round 200 kilograms. And let's say that the merry-go-round has a radius of 2 meters. Right, same one that's in the homework problem. I'm trying to keep it the same. And the one that we practiced on. We did a practice talking about this. I'm going to just a slight modification to make it a little bit simpler. Let's say that I have 2 kids who are standing on the very edge of the merry-go-round, and they are each 60 kilograms. To get us started and just get the brains operating, I'd like you to find the angular momentum of the system while it's spinning. The system, that includes the disc and the 2 children. And I'd like you to find the kinetic energy of the system. And I'm willing to be super helpful. Like the moment of inertia of the merry-go-round is that of a disc. And it has a moment of inertia of 1/2 mr squared. And the moment of inertia of the children, they are point masses because they are standing at the edge of the disc. So their individual moments of inertia would be mr squared. And if you don't recall, angular momentum is I times omega. And kinetic energy is 1/2 I omega squared. So take a second and calculate the angular momentum and rotational kinetic energy of the system. So for the most part, I'm seeing the right things. A few missteps, just a few. So let's start with moment of inertia real quick. The moment of inertia of the merry-go-round is 400 kilograms meters squared. Let's be careful about units here. Okay, kilograms meters squared. What's going on there? There we go. The moment of inertia of the children, there are 2 of them, each 60 kilograms standing 2 meters away. That's 2 squared is 4 times 60 is 240 times 2 is 480. So the children together give a moment of inertia of 480 kilograms meters squared, which gives me a moment of inertia of the system of 880 kilograms meters squared. All right. Any questions about that? Now, this is how I did it. You could have separated it out more. It doesn't matter. But I'm just going to treat it as a system. So when I wanted to find out the angular momentum of the system, then that was going to be 880 times 4, right? Because it's just the moment of inertia times the angular speed. That's, I believe, 3,520. But let's keep careful about the units. This is kilograms meters squared times radians per second. Well, under these circumstances, the radian disappears because radian is truly a unitless quantity and is superseded by the kilograms meters squared. So we'd write this as kilograms meters squared per second. It does not have a special name. Any question about that? All right. So now we'll deal with the energy. Maybe. Well, won't let me do what I want to do, so that's okay. So let's start right here. 1/2 880 times 4 squared, giving us 7040, and that's kilograms meters squared per second squared, which is a joule. All right, we do change the name here. So this is our angular momentum. This is our total energy. All right. That problem isn't what I'm interested in. I'm interested in this problem. The kids walk towards the center. If you remember our conversation from before spring break, and if you don't have this in your notes, perhaps now would be the time to write it down. If there are no external torques on a system, the momentum will be unchanged. This is a statement of conservation of momentum. If there are no external torques on a system, the momentum will remain the same. So in this system, the kids are going to walk towards the center 1 meter. Are they an external torque on the system? No, because they're on the merry-go-round. They are not external to the system. So they walk towards the center. By how much would that change the angular momentum? If you're listening to me, you know that the answer is it wouldn't. Right? If they walk towards the center, they are not an external torque. So the angular momentum of the system stays the same. So right now, they walk towards the center, the angular momentum of the system is still 3,520 kilograms meter squared per second. However, did the moment of inertia of the system change? Yes. So what had to change in response? The speed. So in this case, this is a state of where the angular momentum before the kids moves has to be equal to the angular momentum after the kids move. It's not a collision, but it's a conservation of angular momentum question. In this circumstance, there was a combination of moment of inertia and angular speed. When the moment of inertia changes, the angular speed has to change by the same proportion. There's proportionality here. So take a moment, please, and find the new angular speed due to the kids walking towards the center. This represents the before moment of inertia. You will have to find the after moment of inertia. Because this is pretty straightforward, I hope. I don't have to recalculate this side. We know that the angular momentum of the system is 3,520. The new moment of inertia, well, the platform didn't change. So the merry-go-round is still 400. But the kids are now 1 meter away from the center, not 2 meters away. So they only add another 120 kilogram meter squared. So the new moment of inertia, 520 kilogram meter squared. Follow along, okay? So the moment of inertia went down to 520. That means the angular speed had to increase by the same proportion. So your angular speed should be 6.77 radians per second. Now, this next part's hard, I think, to understand until you kind of see it a couple times. The merry-go-round's going faster now, right? Do you recognize that in calculating energy, if the angular speed increased by the same amount that the moment of inertia went down, then there's going to be a bigger change to the kinetic energy. That the kinetic energy is not going to stay the same. So I want you to find out how much work was done on the merry-go-round by the kids. I want you to keep in mind, I don't know anything about how much force they applied. I have an idea, and we'll talk about that later, but I want you to keep in mind, I don't really know. I do know that we could figure out the kinetic energy after the kids walk towards the center. Because we have the moment of inertia of the system by the time they make it to the center. And we know that when they make it to the center, the system has now increased its speed to 6.77 radians per second. So we can calculate the new kinetic energy. $11,916? Would we agree that's a pretty significant increase to the amount of energy in the system? Now, the first thing I want to point out is I would never ask you to do it this way. I would ask a more esoteric sounding question, like what was the net work done by the kids on the merry-go-round? You would have to translate that as to finding the change in kinetic energy. Because in this circumstance, there's no information about force, although there must be a force acting on the kids this direction for them to be traveling in a circle, right? Something about, I don't know, mv squared over r or m omega squared times r. They have to work against that force to move to the center. That's the force they're working against. We could figure out how much work was done by talking about force, but as they move towards the center, do you realize the force is changing the whole time? Because they're getting closer and closer to the center, and the speed of the system is changing the whole time. So that's a hard calculation. But just finding the change in energy, not a hard calculation, is it? So keep in mind, positive work was done on this system. The kids converted some of their potential energy, chemical potential energy probably in our muscles, to kinetic energy by pumping the system. We talked about, swings and stuff like that. This is how those systems behave. But again, there was nothing external. The kids did the work on the system. All right. You have several problems like this in your homework, but I want to describe a different problem now, okay? To do so, call your attention to something we talked about first semester. And I hope that this is not too big a stretch for you. Do you remember problems that were like this? I have, say, a box, and so let's say that there's an arrow that's flying towards the box. It hits the box, becomes embedded in the box, and now the arrow and the box are moving to the right. Standard collision problem. Does that sound familiar to all of you? So we would have done something like mv plus 0 equals m plus m times v final, right? A standard collision question, conservation of momentum, right? Then there might be questions like if there's friction, that would be an external force on the system that might affect the answer. But if there wasn't friction, then the box and arrow would just be sliding to the right. All seem reasonable? All right. If there was, say, a lip on the table like that, would this collision result in the box moving to the right? No, right? This would be an external force on the box that would keep the arrow in place and have it just embed itself in the box because the box wouldn't slide. All reasonable ideas, right? I'm looking top down on two boxes. They both have the same mass, same velocity. They're moving towards each other. All okay? If they were to strike each other and stick together, can we agree that right now the momentum of the system is 0? Because they have the same mass, same velocity, traveling in opposite directions? So that when they meet in the center, they're just going to come into contact and stop. All good, right? No big deal. Now, instead of two boxes, let's say they're two hockey pucks. Same size, same mass. And I need to draw in something for reference. So here's the line I'm drawing in for reference. Just a reference line. What if I tell you that these hockey pucks have like Velcro, opposite Velcro on each side, so that when they touch each other, they stop and stick together? All good? But what if this hockey puck was right on this side of the line, and this hockey puck was right on this side of the line? So they only touch at the one point. would you agree that if they have the same velocity, they currently have momentum 0? Right? Same mass, same velocity, opposite directions. They're going to meet in the middle. Touch in the middle. They're going to stay in the middle, but they're not going to stay still, are they? They're going to spin about this mutual point where they're in contact. So the question is, obviously these two pucks, before they touched, when they were like this, had momentum. After they touched, they suddenly have angular momentum? Well, angular momentum and linear momentum don't work together. We've said this before. But there must have been some kind of angular momentum in the system because there's no external force on the system, and they end up with angular momentum after they touch because they're spinning in a circle, right? We're going to go over this problem, but I'm going to start by describing angular momentum for what's called a point mass. And I'm going to use the example we did here, right? With the arrow hitting the block. Different example, just so it's easier to see the mathematics. Let's go back to our merry-go-round. And let's talk about a kid who's going to run and jump onto the merry-go-round. If the kid runs directly at the center of the merry-go-round and they jump right onto the merry-go-round here, will they cause the merry-go-round to spin? No. More importantly, will the merry-go-round and the kid suddenly be going this way along the ground? No, the merry-go-round is firmly fixed in place, right? It's got a spindle at the center so it can spin. But when the kid hits the merry-go-round, he certainly applies a force to the merry-go-round this way, but the thing that's attaching it to the ground applies a force this way. This is not particularly interesting. But what if instead the kid was like down here and they ran and jumped here? Now this is a collision. Is the merry-go-round going to suddenly start going this way? No, there's an external force on the system to hold the merry-go-round in place. That applies a force this way. At the same time, the kid applies a force to the edge of the merry-go-round this way. Net force is 0. Merry-go-round and kid stay in place, right? But is the net torque 0? No. This force does not apply a torque to the system. Does this force? Does. So we have constructed a way of analyzing this kind of system and assigning angular momentum to the kid. Because in this collision, the system has angular momentum after the collision. But the kid is part of the system. We don't believe his force is an external force. It's internal to the kid merry-go-round system. So in this problem, we're going to treat the kid as if they have angular momentum. And we're going to develop a way of doing problems like this by saying that the kid has angular momentum. But it should be clear to you, the kid is running in a straight line, right? If they run, say, at some given speed, they're just getting closer and closer to the merry-go-round. They're running in a straight line. So we assign an angular momentum for point masses. Now, this is not necessarily easy to understand, but it's not particularly hard. We're going to use a lowercase l to differentiate this from an object that's rotating, because we know this object is traveling in a straight line. To describe its angular momentum, we describe its momentum relative to a fixed point in space. We're going to pick a fixed point to measure its angular momentum. We did this for linear momentum, but we never stated it like that. We just said it had some velocity relative to things that weren't moving. But now we're going to say this object has angular velocity relative to a specific point in space. We have to pick a point. and you pick a point that makes sense. For example, in this problem, the merry-go-round is going to spin after the kid jumps on it. So it makes sense for this point, the center of the merry-go-round, to be that fixed point in space, because eventually the merry-go-round is going to spin about that point. Now I want you to imagine you're standing at that point, okay? Can you imagine that? And you are looking at the kid. And I'm telling you, look, it's dark out. Shine a flashlight on him the whole time. Wouldn't you have to kind of spin the beam of that flashlight to track the kid as they ran by? This green arrow, as it rotates about that point, is the way we measure the kid's angular momentum. We treat it as if there is a line connecting that point to the kid. And as it spins about that point, we say that that's the angular momentum of the kid. Now, this is physics, so we put numbers to this. And so first, I'm going to connect that line. I'm going to call this R. It's like a lever arm. It's the vector that describes the displacement from the pivot point to the object. The kid himself has linear momentum. He's running. What we say is that the angular momentum of the point mass is that R cross the kid's momentum. It's a cross product because angular momentum is a vector. The direction of spin matters. Now, it's a cross product, which means this is just R times P times the sine of the angle. And that would have to be the angle between R and P. So that would be this angle. Now I know this looks kind of funky. And if you're with me right now, I know I'm going a little fast. Isn't R getting smaller? This makes it look like the kid's angular momentum is always changing. I mean, eventually the kid will be right here, running perpendicular to R. In fact, I would call this R perpendicular. But I'm also noticing that as R gets smaller, the angle keeps getting bigger. Are you noticing that too? You guys are smart kids. Follow me on this, please. You see that right triangle there? Let's do the math on that right triangle real quick. This is our angle. Wouldn't sine of that angle equal R perpendicular over R? Sine is opposite over hypotenuse. So wouldn't R perpendicular equal R sine phi? Okay. How about that triangle? It's a different angle and a different R. But wouldn't it also be that sine of that angle would be R perpendicular over R? We generally don't use these two to calculate the angular momentum. We usually use what's called the R of closest approach. The value of R right there where the kid jumps on. Because I'm not going to tell you where the kid starts. All that matters is where the kid lands on the merry-go-round. So although this is technically how you calculate the angular momentum, in this class, generally we will always calculate it as R perpendicular times P. We will wait until the kid actually gets to the merry-go-round and do that as our calculation for the momentum. Just 60 seconds. If the kid is running towards the merry-go-round and jumps onto the merry-go-round from here, then the kid's angular momentum is the angular momentum of the system before he jumps. And then he is part of the merry-go-round after he jumps. So this would have to be the angular momentum of the system afterwards. This is how you would calculate how fast the merry-go-round is going after the collision. All right?